Okay, so we're going to start the next talk. So dear students, dear teachers, and dear parents, a very warm welcome to this year's Berlin Mathematics Day. My name is Claudia Schillings. I'm professor here at Freie Universität in mathematics, and I'm also a spokesperson for the Cluster of Excellence Math Plus. It's a great pleasure to welcome you all here today and to spend this exciting day exploring this fascinating world of mathematics together with you. A special highlight of our program is the lecture on the work of Gerd Faltings, one of the most important and influential mathematicians of our time. So to introduce this topic to you, we are delighted to welcome a distinguished expert, Professor Dr. Jürg Kramer. Jürg was a professor of mathematics and mathematics education at Humboldt-Universität from 94 to 24, and after completing his PhD at the University of Basel and his habilitation at ETH Zurich, his academic path took him through several international positions before he eventually came to Berlin. There, over many years, he played a key role in shaping both arithmetic geometry and the education and support of young mathematicians. Alongside his research, he held numerous positions of responsibility, including director of the Mathematical Institute at Humboldt-University, spokesperson of the Berlin Mathematical School, and member of the board of the Cluster of Excellence Math Plus. So he's also been deeply committed to teacher education and the promotion of young talent, for example, as a director of the German Center of Mathematics Teacher Education. So since January 1st, 25, he's also the president of the German Mathematical Society. I'm very pleased that he's here with us today to give us insight into the work of Gerd Faltings, a topic that beautifully illustrates how closely number theory and geometry are intertwined. So dear Jürg, we are very much looking forward to your talk, and we sincerely thank you for being here with us today. Thank you.
Okay. Yeah, thank you, Claudia, for the kind introduction, and welcome everybody to this talk, which is somewhat an insider talk, right? We talk to the BMS, but not only, but all the other people are, of course, also very welcome. So I just gave an hour ago this talk for a high school student primarily in German, and now I somewhat repeat this talk in English. I will go maybe a little bit faster than beforehand, and the point is that the work of Gerd Faltings is difficult to explain, and I barely will go into his ideas of proof. I rather stick to the statements. But still, when I have a little bit of time left in this part of the talk, I will try to give an idea of one of his main results, how it is proven, so to say. Okay, so let's start. The motivation, I think, to give this talk here was the announcement of the awarding of the Abel-Preis this year to Gerd Faltings. And so it's mentioned for introducing powerful tools in arithmetic geometry and resolving long-standing Diophantine conjectures of Mordell and Lang. So you already see a little bit, Diophantine is somewhat in some other words means some number theoretical problems, but he solved these problems using tools in geometry. So he used successfully the translation of number theoretical problems into geometry and thus was able to solve the problem. But let me be more specific. So already 1986, Faltings was awarded the Fields Medal, which is somewhat the equivalent of the Nobel Prize at the ICM 1986 in Berkeley. And here is just the first part of Barry Mazur, at the time at Harvard University, of Barry Mazur's laudation on Faltings' work. And what I will do is I will stick to the statement given here at the end of this slide, which states that if K is any number field and X is any curve of genus bigger than 1 defined over this number field, then X has only a finite number of K rational points. So this is a long-standing problem which was open for more than 50 years when Faltings solved it in 1983. And this is the problem I will focus on in this talk mainly, so to say. Faltings did much more than just solving his problem, so he, as was mentioned, he developed the machinery to attack such a number of theoretical problems and solved many more other problems than just this one, even though this one was really a long-standing problem. And let me also mention, I mean, there's only a handful or maybe 6 mathematicians who have at the same time the Fields Medal and the Abel Prize. So it's really an outstanding person, Gerd Faltings, who was director at the Max Planck Institute in Bonn, and still around at the Max Planck Institute there. So here is restated Faltings' theorem, which was formerly called Mordell's conjecture. I don't read it to you anymore. And just to make the notions precise to everybody, we have to clarify what a number field is. Some of you might know, some of you don't. If you're in number theory, of course you know, but if you're maybe more in applied, you possibly do not know what a number field is. What is a curve defined over a number field? What is a k-rational point on this curve? And what is the genus? So let's clarify these notions briefly. So the simplest model of a number field is the field of rational numbers. So I assume that all of you know what a field is. And the field of rational numbers is the simplest number field, and it consists of fractions a divided by b. A, b are integers, b non-zero, and you can add, subtract, multiply, and divide fractions with each other, unless the fraction is 0, of course. So this means it's a field, and I will stick in this talk to the case of rational numbers. Even though I just mentioned, for those who know a little bit of algebra, a number field is simply given by a finite algebraic extension of the rational numbers. So this is the more general notion over which Faltings worked in general somewhat. But those who don't have this algebraic background just stick to Q. Others can think of finite algebraic extensions of Q. So then just to set notations, the natural numbers are denoted by n, the integers by z, and the reals by r. And then what is a curve defined over the rational numbers? Well, we start with a polynomial in 2 variables, capital X and Y, and then we have an expression of this type. You have a constant term, which is given by a0, 0, which is given by a rational number. Then you have the linear terms a10x plus a01y, where the coefficients again are rational numbers. And then it keeps on going. You get the quadratic terms, you get the cubical terms, etc., up to some finite point. And this constitutes a polynomial in 2 variables, and all the coefficients should be rational numbers. And what I assume for the sequel, I assume that the polynomial is indecomposable, it's irreducible. So you cannot factor such a polynomial over the rational numbers into polynomials of the same type, so to say. And of course, the polynomial shouldn't be constant, so to say. So we make this irreducibility assumption. So for example, x plus 1 parenthesis squared is of course not irreducible because you can factor it x plus y plus x plus times x plus y, right? So this is excluded, so to say, in the sequel. And then the curve is given by the set of all pairs in the real plane, in the affine plane if you want, in the affine real plane, such that they satisfy the equation. If I plug in the coordinates x, y into the equation, then it's 0. So it's the 0 locus, the set of zeros of this polynomial. And sometimes you could also even look at it from a complex point of view, because some of you might know there's this kind of analogy between algebra and analysis, that you can view curves as Riemann surfaces, and if you view them as Riemann surfaces, you should take the complex zeros, so to say, right? Okay. So this is an example. You see, it's just a real picture of this 0 set x squared plus y squared minus 1 equals 0. So this is the unit circle, as we know. And there's another example, this kind of curve x squared plus y squared squared plus 3x squared y minus y cubed. So this is a curve which gives rise to this three-leaved rose, this nice picture, so to say. So these are two typical examples of curves. And something it's not meaningful in these two examples, but later on it might be meaningful that we also look at the affine plane being embedded in the complex plane, and then we can even view our curves in projective space, so to say, in the projective plane. Okay, so the third question is, what is a rational point on the curve? Well, it's quite natural. What should it be? Well, we have looked at the curve to be the set of all real pairs x, y, such that fxy equals 0. So now a point which is rational is naturally a point which has just rational coordinates. So, as depicted here, a rational point on a curve defined over Q is a point xy such that the two coordinates xy are rational numbers, so to say. And then an example of the unit circle is the point 1, 0 is a rational point, of course, there, but this point square root of 2 over 2 square root of 2 over 2 is, of course, not a rational point on the unit circle, since square root of 2 is known not to be rational, right? This is one of the famous example one learns first, that one has to extend the field of rational numbers to get the real numbers by adding square roots, etc. Okay, so just as a notation, if I put C parenthesis Q, then I mean just the rational points of the curve, so to say. Good. The last question is the question of the genus. I just mentioned that in this analogy between, or this dictionary between algebra and analysis, that you can view the complex points, the complex solutions of polynomial equations, then you get something which is really viewed two-dimensional. So you get a surface, so to say, and then some of you know what the genus of a surface is. It's the number of holes this surface has, so to say. But the algebraic way to describe the genus is very simple, so to say. We have seen that we define our curve by a polynomial in two variables, which is irreducible. And it has some degree, and the degree is just the maximum of the sum of the indices j plus k, such that the coefficients are non-zero, so to say. So going back to the examples we had, so this is a curve of degree 4, because if you multiply out this x squared plus y squared squared, you get something which is, of course, of degree 4, and all the other terms have smaller degree, and of course the unit circle has degree 2, is a curve of degree 2, right? Okay, so we understand what the degree of a curve is, so it's the maximum of the sums j plus k, where the indices, where the coefficients with the indices jk are non-zero, so to say. So we know what the degree of a curve is, and if C is a smooth curve, then the genus is given simply by this formula d minus 1 times d minus 2 over 2. And now I should explain what smooth is. Well, smooth, I said it in words, has no double points or other strange points. So again, in the example we had before, you see the unit circle is a smooth curve, so there's no points that are special, so to say. But in this three-leaf rows, of course, the origin here plays a prominent role, because it's a triple point, so to say. So if you go along the curve, you pass through the origin 3 times. It's a triple point. So this is some exceptional point, and this is called a singular point. And likewise, you have double points, and we will see also cusps. So these are special points which are not the generic points on a curve, so to say, which are the so-called normal points, so to say. And so if we have a curve which has no singular points, then its genus is given by this formula d minus 1 times d minus 2 over 2, where d is the degree of the defining polynomial with rational coefficients. And if you want to compute the genus of a curve which has singular points, which are finite in number, then you have to subtract from this expression d minus 1 times t minus 2 over 2 the number of these singular points with multiplicities, so to say. So we will see examples later on where we also make these calculations, but anyhow, so that's the genus of a curve from an algebraic point of view, so to say. And it coincides with the genus that you might know from geometry if you look at this curve from a complex point of view and then count the number of holes which occur. Okay, so now coming back to Faltings' theorem, it now states the following thing. So it is a kind of a variant of his theorem. After having clarified all his notions, if I have an irreducible polynomial with rational coefficients, which defines a smooth curve, so a curve without singularities of degree d, then if d is bigger than 3, the set of rational points is finite, because you remember the formula for the genus was this g equals d minus 1 times d minus 2 over 2. And if d is bigger than 3, this means that the genus is bigger than 1. And you remember the initial statement was if I have a curve defined over q, which has genus bigger than 1, then Faltings stated it has only a finite number of rational points. And in other words, it means if the degree is bigger than 3, there are only finitely many pairs xy rational numbers, such that these rational numbers are zeros of this polynomial equation f xy equals 0. So one typical problem, a typical problem is, for example, Fermat's equation. You might know, if I state it in rational numbers, you have x to the d plus y to the d equals 1, and you wonder, this has only the trivial solutions, 1, 0, and 0, 1. And this was proven in the mid-90s, 95, by Andrew Wiles. But from Faltings, we can at least conclude that if the degree is bigger than 3, that then we only have a finite number of points. And of course, then there's a major step to prove that 1, 0, and 0, 1 are the only rational points, but still, he did a major step towards the solution of Fermat's problem, so to say. Another issue, of course, is when we now keep on going, it could be that such a polynomial equation has no rational solution at all. So you know from school that we had the example already, square root of 2. If you look at the equation x squared minus 2 equals 0, it has no rational solution, because we know that x squared equals 2 has a solution plus minus square root of 2, which is irrational. Okay, so but anyhow, to give a feeling, because the degrees 1, 2, and 3 are not covered by Faltings' theorem, let's look at what's happening in degree 1, in degree 2, and degree 3 first, before we come back to Faltings' domain where the degree is bigger than 3. And then curves of degree 1 are simple. These are linear functions, so to say, linear polynomials, which are of this type, ax plus bx plus by plus c, where now in our convention ABC, the coefficients are rational numbers. And of course, in order to have at least degree 1, a or b have to be non-zero, so I assume a is non-zero. And then immediately you see that such a linear polynomial has infinitely many rational solutions. You simply take y equals as lambda, a rational parameter, which runs through all the infinite amount of rational numbers. And then you just adjust x by this formula. You solve the linear equation by this formula, minus b lambda plus c over a. A is non-zero. This gives you the corresponding x's, and if you make the count, since y has infinitely many possibilities which it runs through, of course countably many possibilities, we get that the number, so this is the sign for the number of this set of rational points, this is an infinite. This is infinite. So we, in contrast to Faltings' result, where we talk about the finitude of solutions, we have infinitely many solutions in degree 1. I think this was easy. This is well known. So now let's look at curves of degree 2. And then the first assumption, to simplify life a little bit, you have, of course, your polynomial equation. It has three terms of degree 2, x squared, y squared, and the mixed term xy. Then it has linear terms xy, and then it has a constant term. And then by completing the square, you can reduce the situation. You make a completion of squares and make coordinate transformation with rational coefficients. So you can reduce your equation for the subsequent considerations in the form that you simply have the two terms x squared and y squared with the coefficients a and b, and you have a constant term which I normalize to -1. It could also be that you have to normalize it to +1, but this just changes the shape from an ellipse to a hyperbola, right? So this is the only change. So let's stick with the ellipse. It's easier to depict here on the slide. So I have this quadratic curve. I assume a and b are non-zero. And now we wonder, does this curve has finitely many or infinitely many solutions? And of course, the first issue is that we assume it has at least one solution. As we saw, this example x squared equals 2 is an example where we have no solution, so it's a non-trivial assumption we make, but let's assume for the circle that we have at least one rational point. And if I make this assumption, I will show you in a minute that then the number of rational points is again infinite, like in the case of the curves of degree 1. And this is a concept that we used the previous result to deduce this claim for the curves of degree 2, like we use tools in linear algebra to solve problems for quadrics, so to study quadrics, so to say. Okay, so we have our rational point P on our ellipse, and now we will prove out of this P I can construct infinitely many rational points of this ellipse. And what I do is I take an auxiliary line L, and the line L should be a line which has rational slope. In other words, for example, assume that the line goes through the two rational points Q1 and Q2, so points with rational coordinates. So it's a line as we considered it in the case of curves of degree 1. And then I choose, for example, these 3 points on the line which have rational coordinates, and I know from the previous reflection that we have in fact infinitely many rational points on the line L. And then what I do is I connect these points with the given point P on the quadratic curve. And then of course we know, since it's a quadratic curve, we have to have intersections of these connections between Q1, Q2, Q3 with P. We have to have intersecting points with the ellipse. So my claim is now that these points R1, R2, R3 are also rational, so to say. And the argument I will do in a moment in a quantitative way, but let's just make the reflection briefly. You will easily follow. So this point Q1 has rational coordinates by choice. P also by choice has rational coordinates. So the line through P and Q1 is a line as we considered it when we studied linear polynomial with rational coefficients. Okay, so then we have a line, we have a polynomial equation with rational coefficients, ax plus by plus c equals 0, which describes this gray line. And so we have to intersect it with this ellipse. And so in order to find the x and y coordinates of this intersecting point R1 or R2 or R3, what we have to do, we have to substitute the linear equation into the quadratic equation. Say we substitute y, and then we get a quadratic equation in x, and then we solve this equation. It has 2 solutions, but we know one solution is the x coordinate of P, and so which is rational, and then The other x-coordinate also has to be rational because the quadratic equation will have only rational coefficients, and then it's Vieta's theorem which tells us that this has to be the case. Okay, so in other words, what have we done? Basically, if we view here in our with our eyes the infinitely many rational points on this rational line, then to each of these points we have a rational point on the quadratic curve and vice versa, so to say, because if I connect P with R3, then I get the rational point on the line. So what we have established is a bijection between the rational points on the line and the rational points on the quadratic curve. And since we have this bijection, and we know that on this curve L we have infinitely many rational points, then the number of the rational points on the ellipse also has to be infinite. So this proves the claim. So curves of degree 2, which have at least one rational point, also have automatically infinitely many rational points. And this is just the quantification I promised. So if you take specifically the unit circle, which we had before, and for the line L, the auxiliary line L we had before, you take the y-axis and you vary by varying t through all the rational numbers, all the rational points on the y-axis, and you connect this point -1, 0 with this point 0t, you parameterize all the rational points on the circle in this way, because if you make the computation, you compute the straight line between these 2 points, and then you intersect with the circle, you drop out, you get this. So this is just a slide where you do the computation. The line is given by y equals t times x plus 1. You substitute y into the quadratic equation from the unit circle, and then you solve, and then you see by Vieta's theorem that a solution, the second solution is 1 minus t squared, 1 plus t squared, which is depicted here, this x-coordinate, and then you just complete the square, and then you get the y-coordinate, right? Okay, so this is, by the way, this of course allows you to determine all the Pythagorean triples, but I don't want to go into that. Let's rather go to elliptic curves now, or first cubical curves, and elliptic curves is a subclass of cubical curves. Because now we understand curves of degree 1, curves of degree 2, and now we want to understand curves of degree 3, which are to some extent at the threshold when we think of Faltings' theorem, because then the degree gets bigger than 3. Okay, so in general, this curve is given by a cubical polynomial like this, with coefficients from a going up to j. And we assume, again, for simplicity that, or what I mean by simplicity, we just assume to proceed that it has at least one rational point. And since we are allowed to think projectively, we can assume that this rational point is far out at infinity, the point at infinity. I will show you in a picture. So when we make this assumption, you can make by completion of the squares, the Tschirnhausen transformation, and all these things, then you can reduce this complicated equation having almost 10 or something like that coefficients to a more simpler object, which is of the form y squared equals x cubed plus ax squared plus bx plus c, where you can even assume the coefficients to be integers, so to say. Okay, so this is the so-called Weierstrass normal form of a cubical curve, which has a rational point, where the rational point sits at infinity when I put it into this normal form. And if the curve is smooth, I will show you in a minute the picture of a smooth curve and of non-smooth cubical curves in Weierstrass form. But when it's smooth, it's an elliptic curve, and that's an example of an elliptic curve. You see there are no singular points, no double points or triple points or something like this. So this is the curve y squared equals x cubed minus x plus 1. This is a cubical curve. It's smooth. It's in Weierstrass normal form, so it's an elliptic curve. And the point at infinity is somewhere up here, or les extrêmes se touchent. It's also very far down, so to say. Good. and these are two examples of cubical curves in Weierstrass normal form which are not smooth because here you have a double point, y squared equals x cubed minus 3x plus 2, so you have this double point here, or you have this cos y squared equals x cubed. So these are cubical curves which are singular, and just doing the training for the genus computation. So if this is a smooth curve, it has degree 3, obviously. And then you remember the formula in the smooth case for the genus was degree minus 1 times degree minus 2 over 2. So 3 minus 1 times 2 minus 1 over 2 is 1. So this has genus 1. And in this case, well, we have singularities, and I said also do first d minus 1 times d minus 2 over 2, which is also 1. But now subtract the number of singularities. We have one singularity each, the cusp and the node, so we subtract 1. We cannot subtract more. The genus has to be bigger or equal to 0. So these are curves of genus 0, and that's why thinking of the previous reflections, if they have one rational point, they will have infinitely many rational points. Okay, so but now let's focus on elliptic curves, so on cubical curves with a rational point sitting at infinity, as we have agreed upon, and which are smooth. So then these curves of degree 3 are special because you can do addition on these curves. You can add rational points. Namely, you do what we have done before. It's just the only thing you can do. You have points on curves, and then you can make straight line through 2 points, and then you can intersect, so to say. So that's the tool we have used successfully for degree 2, but now we can also successfully use it for degree 3. We have two rational points, P and Q, and we make the straight line through it, and then we reflect, and we get the point S, which we call the sum of P plus Q. And the point is, this operation obviously is commutative, right? And with a little bit of effort, it's not completely trivial, but with a little bit of effort, you can even use Mathematica or something like that, but it's even there, it's a little bit involved. You can prove that it's associative, this operation. So on these rational points on a elliptic curve, you have an addition law, which is commutative and associative. But this is, of course, fantastic. If you have one rational point, you can start making lots of points by just adding them to itself, so to say. But then there are two options. Either after finitely many steps, you return to P itself, or you never return to P itself. And in the first case, you get out of P finitely many points. In the second case, you get infinitely many points. This is also in the direction we want to go, right? And Mordell, whose name was already mentioned, I mean, Faltings proves Mordell's conjecture, but this is Mordell's theorem. So Mordell proved if we have an elliptic curve given as we have agreed upon, y squared equal x cubed plus 8x squared plus bx plus c, an elliptic curve, so a smooth cubic, given in its Weierstrass form, then the nature of the rational points is not quantitatively, but qualitatively very clearly described. There exists finitely many points, P1 up to PR, such that all other rational points are obtained by successively adding P1s to itself, etc., up to MR times PR, so to say. So to be precise, I should even write that the M1 up to MR are in the integers. Just to elementarize, I only wrote N, but to be honest, there should be M1 up to MR to be allowed in the integers. And so the ones who know a little bit of algebra, they understand what I have shown. The number of rational points is an abelian group, because we have an addition law, which is associative and commutative. And what we have proven that this abelian group is finitely generated. P1 up to PR are the generators of this finite abelian group. so to say. So this is in the algebraic notion. And then the point, what I said before, I mean, depending on if all P1 up to PR only give rise to finitely many points, then of course in this way I can only get finitely many points. But Mordell also gave examples that there could be one of the PR giving rise to infinitely many points. So depending on the equation we start with, on elliptic curves, we have both possibilities. The elliptic curve could be of the shape that it has only finitely many rational points, or it can have infinitely many rational points. So it's really on the threshold. We go from degree 1, degree 2, where we have infinitely many rational points, if we have one at least. You go to degree 3, where if we have at least one rational point, which we set at infinity, then we have the possibility, both possibilities, either finitely many or infinite many rational points. And then, as we know, Faltings then showed that if we go beyond degree 3, then the number will always be finite, so to say. And here are two examples. So this is the first example. So I used the algebraic notion. So the abelian group C of Q is generated by this point 2, 4, coordinates 2, 4. And infinity, infinity means the point at infinity. And this curve is generated by Q, and it's of rank 1, so it's a curve which has infinitely many rational points. And just in the first example, you can easily see how things work. You take Q, you take the double of Q by taking the secant at Q, which means the tangent. It intersects the curve in the origin. Then you reflect, nothing happens. You get 2Q. And then you combine 2Q with Q. You make the intersection, you reflect. And then you get the point 3Q. And then if you add 3Q to Q, you have the vertical line which intersects the curves at the infinite point. You reflect, you are still at infinity. So that's the infinite point. And then if you add 3Q to 2Q, then you get back to Q itself. So, I mean, this is a curve which is cyclic of order 4. It's the abelian group Z mod 4Z, so to say. Okay, so this is the example of finitely many rational points, and that's the example, I mean, I just show this picture to show that, yeah, it will have a dense number of points which accumulate to each other. Yeah, and then we get to curves of degree bigger than 3, and we arrive at Mordell's conjecture made in 1922. You know the hypothesis. We start with a polynomial of degree d bigger than 3, which is irreducible and gives rise to a smooth curve. And then the conjecture is by Mordell that it only has a finite number of rational points. This is an example. It's a hyperelliptic curve of degree d. And here is a picture of Mordell and an important person, André Weil, which will come in a second. His name will come back in a second. And this reminiscent of André Weil when he was doing a thesis by the end of the 20s in the last century. In his commentaires, in his collected papers, he writes, "Une autre circonstance faillit me retarder beaucoup." So another circumstance set me back in my work since I had the ambition to prove Mordell's conjecture. So Mordell made the conjecture 22. He did his thesis around 27, 28, so a couple of years later. So he tried to prove it, and then he asked his advisor, Adamar, and Adamar told him, well, continue to work on it. You don't have to publish a half result, so to say. So then he tried, but he gave up, and history tells us, well, it needed more than 50 years to solve the problem until Faltings then solved it, so to say. So Faltings' theorem is now the statement that Mordell's conjecture is true, not only over Q, but over any number field, so any finite algebraic extension of Q. And what I say here, I mean, it's difficult to now give you an idea of Faltings' groundbreaking ideas, how to solve the problem, so to say. So he didn't basically work with the rational points. He used the rational points which gave rise to objects which he then somewhat classified, and then found out that the classification leads to a finite list. And in that way, with this detour, he found that Mordell's conjecture is true. But about 10 years later, 1990, Enrico Bombieri found a somewhat elementary proof which really deals directly with the rational points. And in the last 5 minutes or so, I will try to give you a glimpse at Bombieri's proof, so to say. So what we need is the height of a rational point. So Faltings also used the notion of height, but in a more general sense. But we just use the height of a rational point. So we have a curve. We have a rational point with coordinate xy. We write xy as fractions a over b, c over d. And the height of the point is nothing than the maximum, the logarithm of the maximum of the absolute values of these numerators and denominators a, b, c, d. This is the height, the logarithmic Weil height. Here is the name Weil again. This goes back to André Weil, which was on the picture before. So I will just talk about height. I dropped the logarithmic. I will also always look at the logarithmic Weil height and just talk about the height h of p of such a rational point. And then the height has a important property, is the Northcote property, which says that if the set of rational points on a curve with bounded height is finite. And this is simply to prove in our case when we just work with the rationals. Since, just look what I have written above. If I look at the number of rational points with bounded height m is a positive real number, so to say, well, then it's the number of all p in C of q, such that the log of the max of the absolute values a, b, c, d is bounded by m. So I take the exponential, so you have the number of p such that the maximum of the numerators and denominators in absolute values are bounded by the exponential of m. Exponential of m is a finite number. And now if you have a box of size exponential of m, a box of dimension 4, and you search in it the integers, so to say, you only have finitely many integers. You cannot have more. So that's the Northcote property of the height as simple as possible. And then this you can all generalize. This is André Weil generalized to any number field, all these facts. Okay, and now another important notion, and that's something Faltings used extensively, is the Jacobian of the curve C. This is an abelian variety, so Faltings dealt with abelian varieties. We just used the Jacobian of a curve. Now I have to explain briefly in 2 minutes what the Jacobian of a curve is. So it's not as difficult. So we take our smooth curve given by our polynomial. We keep in mind the degree, and we also keep in mind, since the curve is smooth, we can compute the genus in terms of the degree, d minus 1 times d minus 2 over 2. And our goal is, the main goal in Bombieri's proof is that you want to embed the rational points in a Euclidean vector space. Now I have to compute this vector space, and this is related with the Jacobian. So this is the recollection of the genus, and now I come to Jacobian. Okay, the characterizing properties of the Jacobian are basically the followings. So the Jacobian quote is roughly equal to the g times the curve itself. So it's some g-dimensional algebraic object, algebraic variety, I should say. And the tilde means that if I take a g-tuple, I do not care about the order of the elements there. So it's the curve c times with itself up to orderings, so to say. So this is the Jacobian, roughly speaking, and quote, roughly speaking, is not a precise definition, but it's true up to codimension 1, so to say. Anyhow, it's basically a possibility how you can easily picture this object. You just take the g times the curve with itself, and you don't care about the ordering. And now something which you don't understand from the first characterization is the second one. The Jacobian is somewhat the generalization of an elliptic curves to higher dimensions. So we learned for elliptic curves that we have a law of addition there, and on Jacobians you also have this. You don't see it from the first characterizing property. You simply have to believe it to me. And the point is, if g equals 1, if we have an elliptic curve, then of course the product is just Jacobian of c is then the elliptic curve itself. There you really have the equality, and there you also see that you have the addition law, which I explained. And this is a generalization of the concept to higher genus, so to say. And then, last but not least, you have an injective map. You can inject the curve into its Jacobian. So to say this from the first characterizing property, this is not a deep thing, but you just have to a point P, attach P, etc. P, right? There the ordering doesn't play a role. So you see the embedding there. Okay, now André Weil, whom I mentioned already, proved that Mordell's theorem, which I showed that the rational points on elliptic curves form a finitely generated abelian group. He generalized this to the rational points of the Jacobian, so to say. So basically, the rational points on the Jacobian, you just take the rational points of the curve g times with itself, so to say, and then you have the rational points of the Jacobians, you have the addition law, and then the question makes sense, so to say. And he proved in generalizing Mordell theorem that the rational points on the Jacobian form a finitely generated abelian group. That's what I just said. And the point is, if you now take the tensor product with the reals of a finitely generated abelian group, what you get is a finite dimensional vector space, real vector space. So to obtain an Euclidean vector space, you need a scalar product, so to say. And the scalar product we obtain in the following way. So what I just said, tensoring kills only things of finite order. So the point is the rational points embed into our real vector space, and what we lose is only finite amount of information, so to say. So when we talk about finiteness theorems, this doesn't play a role. And then we have our norm on a vector space, and the norm is basically nothing than the height. This quote means up to something which is bounded. Okay, so we take a rational point, we embed it into our real vector space, and the norm of this object is given up to some finite amount by the height of the point itself. So once you have a height, once you have a norm, you have a scalar product, the well-known formula, right? Okay, so in this way, we have embedded up to finitely many points and our rational points into a Euclidean vector space. And that's now the crucial thing. Here comes Bombieri's theorem. So he proves there exists a positive constant m with the following property. If I have on my curve two rational points, such that the norm of the embedded point P is bigger than m and the norm of the embedded point Q is bigger than m times the norm of the embedded point P, then the cosine of the angle between the vectors given by phi of P and phi of Q, so these are elements in the Euclidean vector space, is bounded by 3/4, which roughly means, since 3/4 is, 0.75, so it is close to 0.707. So roughly means that the angle between phi of P and phi of Q is roughly bigger than pi/4. So if this inequality upstairs holds, the vectors defining phi of P and phi of Q have somewhat be far apart from each other. So note that in order to prove this theorem, you essentially use that the genus is bigger than 1 or that the degree is bigger than 3. That's here where it's essentially extremely used, this notion. So now if you make a picture, what you have your vector space V, your Euclidean space, you have your point V of P embedded and phi of Q embedded, and I have subdivided my vector space into cones with apex pi/4, something like. And you see now I have depicted my 2 points in the same cone. This will have a constraint on the initial inequality, namely now we use in the next slide the negation of Bombieri's result. I use that the angle between phi of p and phi of q is not bigger, but less than pi over 4. And then his theorem tells us that phi of q cannot be too far apart from phi of p. And the point, this constraint then leads that in this cone, outside of the circle of the ball of radius m, outside you can only have finitely many points. I mean, you also need the Mumford's gap principle here. But anyhow, because Mumford's gap principle tells you that the points have to be, in the cone have to be somewhat far apart, and this is the contrary, they cannot be too far apart, and this somewhat tells you there can only be finitely many points in such a cone outside the ball of radius m. Inside the ball of radius m, we have finitely many points because of the Northcott property, because since the norm is bounded by m, means the height is bounded by m, so Northcott's property tells us within the ball of radius m we have finitely many. Then with Bombieri's theorem, in each of the sectors we have finitely many, so in total finitely many, and this gives you a little bit an idea of the proof of Bombieri. So now I have stretched time a little bit, but I thank for your attention.
Okay, thank you very much for this very amazing talk. So do we have any questions?
Everybody's tired
Yeah,
now.
so Christian.
Okay. No. No, from Faltings' word, I don't think so. No. Yeah, but one thing, if you say this, at least, I mean, Bombieri's proof is giving you some kind of a concrete upper bound, how many rational points you can have outside the ball of radius m in the cone. This is at least somewhat quantitatively. I mean, the bound is pretty large, but still it's quantitative. But of course, you do not know what's happening inside of the ball. You just know by Northcott it's finitely many, but you don't know how many. Because this was also a question in the last talk, can one give a bound? At least there's a partial result possible here. Do you know how many points you have in such a cone outside the ball of radius m?
Do we have any further questions? Yes, please.
How does this bound and this cone property change when you go up the number field?
I don't know by heart precisely, but the degree of the number field will play a role when you make this bound, all these things. But everything can be done over a number field. This is not a big, the idea is the same. Of course, the bounds will change. They will take into account you try to bound always everything in terms of the degree of the number field. I said a number field is a finite algebraic extension of Q, and finite algebraic means it's a vector space over Q, which means it has a dimension, and this is the degree. And in terms of the genus, degree and the genus, you make your bounds of the number of points. Yes.
Okay, thank you so much. Do we have any further questions? No, it doesn't seem to be the case. So let's thank Jürg once again for this very nice talk.
Thank you.